Hey, Evan.
Hey,
How's it going?
good. How are you doing?
Can't complain.
Good. Yeah. Yeah, so thanks for
Hey,
inviting me. I think this will be fun.
likewise, about 90 people signed up,
Yeah,
and
that's amazing. I guess we'll see how many turn out, but that's a lot. So,
usually something like the square root.
okay. Yeah.
But yeah, that's a high number for sure for what we usually see. So thanks for coming. Yeah, is there anything you want to test or anything like that?
Yeah, I guess I can go ahead and share the screen that I'm going to share and we'll see if that works. So, okay. My plan here is to just work through a notebook.
Oh man, yeah, definitely shouldn't have said square root. That's not right at all. That only works when you have like 30 or so. Yeah, like 40 or 50 people usually come to these things.
Okay.
Cool. All right.
Yes, does this work? Can you see my screen and stuff?
Yep, it's nice and readable.
Yeah,
Uh,
font's big enough? Okay.
Now, Zoom, one thing with Zoom though is that everybody will have like the little icons on the side of the screen.
Hmm.
So I don't have a recommendation, but um, yeah, like, so for example, I can see graphs, but not what presumably is relations, just
Is
due to the default
does
placement.
that does that fix it or is it still
Hmm. Yeah, actually, this may not be something you can fix,
I
but
mean, would it help to actually exit full screen and then does this make it better?
Ah, right.
Is this
So, I mean, that's one workaround, of course, and often what I end up doing. But yeah, anyway, just FYI, when you have the whole screen, they'll have the little floating thing around too. So,
okay? So is this actually better than before to have it in this mode?
hold on. Good question. I don't even know what this mode is. I think I may have exited full screen at the same time you are. So now I can't get it back.
Okay.
Maybe you should just disregard everything I was
All
saying.
right. Well, I'll try full screen and hopefully someone can complain if you can't see anything.
Yeah, I think the issue is probably always going to be on the client side, whoever's watching it. Um, yeah, okay, looking good. So how are things at Topos?
Good. So we're just officially starting, this year. Although, of course, Brendan and David have been working hard for I think like 2 years to get to this point. But yeah, it's going well. It's fun to see things take off. Topos will be starting its own colloquium series pretty soon. I think maybe starting next month. I think so. It'll be good.
Cool. Everyone. As is customary, we'll just wait for a few minutes while everyone connects. Oh, so droppy. While we're waiting, if people want to introduce themselves, say hi, that kind of thing. You know, in a physical meetup, there'd be pizza and drinks, that kind of thing, socializing. Anyone want to say hi?
Okay, I'll start. My name is Ed White. I'm joining from the Boston area, and I had the great opportunity to watch a seminar given by Evan at MIT a year or so ago.
Hi, Ed.
Hi.
Thanks for coming again.
Yeah, cool. Anyone else want to say hi?
Yeah,
Introverted
this
crowd.
is Mark.
Oh, there we go.
Yeah, hi.
Go on.
I'm Mark. I do a lot of wrestling with data frames and data tables in R, and I'm always concerned with compact representations, especially for getting onto the coprocessor. So I'm very curious what's going on in your world.
No, that's great. That's very good motivation for this talk. So that's fantastic.
Cool. Anyone else?
I suppose I could introduce myself. I'm not sure really what to say about it other than that category theory is sort of an interesting topic and its applications in a scripting language or whatever you want to call Julia. Julia is kind of a strange beast. It's not really a scripting language, or it's somewhere in between everything. It's because you can see the compiled assembly and so on. And but anyway.
That's right. It's really sort of a hybrid. It kind of on the surface looks like a scripting language, but it's actually really more of a compiled language in its implementation. So.
All right.
Cool. Other folks want to say hi?
Philip,
Hey.
I'm from Oracle, and I taught for years at UT also, but I'm very interested in the possibility of this working with RDF graphs, because I build a lot of implementations using a combination of SQL and PLSQL and RDF.
Yeah. You know then I think this will be interesting to you because it's as we'll see here at one of the big themes is how graph data structures and relational databases are sort of can be seen from a unifying perspective. So
Very good. Very good.
Cool. Other folks want to say hi?
Hello. I could briefly say, oh, somebody else going? I'm Josh. Go ahead.
You go.
Okay, thank you. I'll be quick. I'm Josh from Uber. I've done a bit of work with Ryan relating to graphs and category theory, and I am interested in learning about C-sets.
Very cool. Thank you for coming.
I can't tell if that's someone else wanting to say hi or just background noise, but yeah. Anyone else want to introduce themselves?
Hello, I'm Serge Boroday. I'm from Montreal. I'm Python and Ruby developer, and here's Julia will replace Python for scientific computing, so that's why I'm here.
Cool. Cool. Sounds good. Thanks for coming.
Other folks, we're still getting people trickling in up to 22 now, so happy happy to, oh, there's another one, happy to wait a little bit longer if more people want to say hi.
Hi, my name's Chris. I work at Confluent, and this just seemed like an interesting talk. It's outside, most of the stuff's outside my wheelhouse, but always interested in hearing new things.
Great, great.
Cool. Yep, people still trickling in, so other folks want to say hi? Or I guess that was ambiguous. While we still wait for people to trickle in, are there other people who want to introduce themselves? Okay, then yeah, I guess we should go ahead and get started. People come in later, they can always get the recording later, which on that note, this is being recorded and the link will be posted on the meetup page afterwards. So anyway, with that out of the way, a warm welcome to Evan, who we all know and love for things such as this. And so yeah, take it away.
Thanks very much, Ryan. Yeah, so and thank you all for coming today. So in this talk, I'm going to explain some of the work that I and others have been doing in Catlab to implement C-sets, which are kind of a family. The way we think of them is that they're a family of data structures that encompass things like graphs and data frames and aspects of relational databases in one sort of framework. So, so I'm going to do this talk more kind of in a tutorial style. So I have a notebook here. We're going to go through it, and it'll be sort of more from a programming and engineering perspective rather than a mathematical one. So everyone has their own opinion about these things, but hopefully that works well here. So feel free to interrupt me with questions. I can't really look at the chat while I present, but you're welcome to just sort of butt in and ask a question. So, okay, so so as I said, we'll be looking at a couple different kinds of families of data processing tools, and so some of them are data frames, also known as data tables. You've probably all heard of these. Data frames originated in the programming language S, which eventually became R, but now they're available in pretty much every data analysis environment in some form or another. So in Python, they're provided by Pandas, and in Julia, provided by a package called data frames, as well as some other packages. So another common data structure that shows up all over computer science, including in data analytics settings, are graphs. So like in Python, one of the most common libraries fits is NetworkX. In Julia, there's a package called light graphs. And then there's also relational databases. So if you've been coming to this talk series, I'm sure you've heard lots about those. So relational databases are best known through their incarnation as SQL databases, but the concept of a relational database is more sort of general than SQL. It's really a particular data model. And so, for example, you see similar ideas in logic programming languages like Prolog. And so one of the things that, one sort of motivation for this work is that these are all familiar tools and ideas, but in practice, they're often considered to be sort of like disjoint, that they inhabit separate universes. So like, the data structures that you use for working with graphs or data frames are totally different. In the case of relational databases, they often exist in sort of standalone systems. So like you can interact with the SQL database through queries, and it's sort of siloed, whereas things like data frames are mostly sort of in memory. And so there's interoperability sort of challenges there in bridging the worlds of like in-memory data analysis and database systems. So one of the really neat things about category theory from an applied perspective is that it actually suggests a unifying viewpoint for these different ideas. And the mathematics of category theory for relational databases specifically is by now pretty well understood, and people like David Spivak and our host Ryan and a number of others have worked on this. And so in this talk, what I'm really going to be talking about is one way of trying to implement or instantiate these ideas in the Julia package Catlab, which I develop along with others. So and so we'll start from in the unifying idea here is C sets. So that's just it's another name for a certain kind of functor. So category theorists might call these Copri sheaves, but we call them C sets because it's a bit shorter. And so the definition of a C set, if you know what a category and a functor is, and if you don't, that's okay, because we'll see here that it's like a pretty intuitive way to think about this. But if you know what those things are, then a C set on a small category C is a functor from that category C into the category of sets and functions. So the way that we think about this in this sort of application area is that we think of the category C as defining a schema of some kind, and the functor then out of this category is instance data attached to that schema. So it's an actual database on that schema. So if you so if you want to read a lot about this perspective, David Spivak wrote a book called Category Theory for the Sciences, where he develops this sort of at great length with lots of examples, if you want to see that. So, but we'll look at it here sort of more from a coding perspective. So one of the simplest examples of this paradigm, but one which is actually extremely useful already, is graphs. So you can get graphs out of this framework by taking a particular kind of schema, and where so as a category, it's the category with two objects, E and V, which we think of as representing edges and vertices. And then it has two generating morphisms, which go from edges to vertices, and those represent the source and target vertices that every edge has. So these are actually what category theorists would just call this graphs, but you might prefer to call these directed graphs or even directed multi-graphs, because they can have self-loops in multiple edges. So in Catlab, the way you would define this schema is by what's called a presentation. So this is a concept from algebra, but we can also just think of it as a way of writing down a schema. So we're going to declare these two objects, V and E, as well as the source and target morphisms. So in general, a presentation has generators, which are the objects and morphisms. You can also have what are called relations, which are equations that relate them, but this is a simple schema where we don't have any relations, so that's good. And so this object, this is a macro which just defines some kind of convenient syntax for this, but it returns an object called schema graphs, and this just is a data structure which encodes this simple information. So for example, we can get the morphism generators and see that there are these things called source and target. So what Catlab provides is a facility for taking one of these schemas and defining a Julia data type which represents C sets on that category C. So for example, to define graphs, we would make this call. So we're going to say, give me the C set type that corresponds to this category or schema that we've defined, and I'll say a little bit later what this indexing stuff is about. But and we're not going to actually execute this line here, because this is in fact exactly how graphs are defined in Catlab's standard library, which includes a variety of flavors of graphs. So this goes to show you there's no, I'm not cheating here at all. This is actually how we do it. So we'll just, instead of running that line, we'll use what comes with Catlab. So we have this graph type. And so so here I'm showing how you can instantiate a graph using Catlab's general interface for C-sets. So we can add some parts here. So I'm going to add 4 vertices, and then I'm going to add 3 edges specifying the source and targets for those edges. And so you can see here that like when this object is displayed and showing me that I have, okay, a C-set with 4 vertices numbered 1 through 4 and edges numbered 1 through 3. So for implementation and efficiency reasons, it's convenient to always have a consecutively numbered parts in your C set. So this is just a sort of an aside. Like whenever you're designing like a graph library, there's always choices about how you deal with these things. For example, in Network X, like you're allowed to give arbitrary IDs to vertices, but we find it a bit more convenient to enforce this. And then if you want to attach labels, we'll see how it seems like that can be done shortly. So in any event, we can see already that the display of this already is looking like a table. So the edge table consists of 3 edges, and we can read off from it what are the source and target vertices of those edges. So we can see here what this graph looks like. Think about it for a second. You can see that this defines like a graph that you might call a directed fork. And so this bottom picture actually shows the edges. Okay, so another departure from, so if you worked with graph libraries, it's often the case that like they require that the graphs be simple, meaning that you don't have multiple edges. So in this setup, there's sort of a very uniform treatment of all the parts of a C set. So like the edges gets IDs too. So this is a little bit different than a lot of graph libraries. So we can see that here that these edges are identified uniquely by IDs, just like the vertices are. Okay, and so Catlab's standard library has all sorts of helper functions for graphs, right? So instead of writing this code with add parts, you can create the same graph like this by using the functions add vertices and add edges. And I just want to mention this because sure, there are these functions, but they all just wrap the C-sets API. So like the core accessors and mutators for graphs in Catlab are all basically one-liners that just sort of call into this general machinery. So like you can very quickly sort of build out that API. So the API.
Hey Evan, can we pause for questions now that we're seeing some examples?
Yes, definitely.
Anyone? Questions, comments?
Sorry, this is my first time joining this group's meetings.
Nice to have
So
you.
I might sound like I might this is going to be a dumb question, but how familiar should I be with category theory to really understand this in depth?
Well, it depends kind of how much you want to know. Like, it is my belief, or at least it's my hope, that like you could use this C-sets library as like a tool without knowing very much about category theory at all. I mean, partly that may require more efforts in making good documentation and stuff like that. But ultimately, I don't see that there's any fundamental obstacle to having this sort of, these tools be like accessible. Just, I mean, like people like, like defining a schema, you don't really have to know that it's a category, for example, to kind of understand like what data format is being encoded by like this schema. Now, if you really want to like, obviously, if you want to have a deeper understanding, it's always good to learn more math, and that's fun. But yeah, so it's kind of a long-winded answer, but yeah, hopefully you can follow along for at least a lot of the parts of this talk without knowing too much category theory. And if not, maybe you can tell me later, and then I can figure out how to maybe explain it better if that's not working. But any other questions before I go on? Okay. So, okay. So the core API for CSETs is actually quite simple. There's really only there's like a couple primitive operations, and on top of that, you can build all sorts of stuff. So, so there are functions to add and remove parts. Okay, so the way this works is that like, basically the objects in your schema, the types in which you can think of as types, tell you what kind of parts you can have. And so, for example, you could have vertices or edges in a graph, so you can add and remove those things. The morphisms in the schema, I like to think of as like subparts of a thing. So like an edge has two subparts. It has a source and a target vertex. So you can get and set those with these functions, subpart and set subpart. And it also, you can use indexing notation, as I'll show later, as sort of a shortcut to this. And then there's also this function called incident, which basically, again, sort of the nomenclature here is sort of based on like a kind of a geometrical kind of picture of CSETs, which in some applications makes more sense than others. But in any event, the incident function gives you the pre-images of these subpart functions. So, and I'll show you that may not be very clear. I'll show some examples of what that does. So to illustrate how these things work, like the target function, which given remember that edges, just like vertices, have numbers. So like to get the target vertex associated with an edge, you can use subpart like that. And then maybe a bit more interesting is, what does incident do? So the incident basically says, so source is a function that goes from edge to vertex, but incident goes in the other direction. So given a vertex, namely vertex 2, find all the edges which have that vertex as its source. Okay, and so if we look at the graph here, so vertex 2, edges 2 and 3 have that as source. So the result of this is, so incident returns a list of things. So we see 2 and 3 here. Okay, and this is where indices come in. So like, if you didn't have any sort of mechanism if you didn't actually store that information or cache it somehow, you'd have to do sort of searches through all of the edges to answer this basic query. And so, and that would make traversals of the graph very slow. So the point of saying index here is source and target. What we're saying is like, keep track of the pre-images of these things. When you add and remove and mutate edges, track that information, so that these lookups are basically done in constant time. So with that, like you can implement like familiar functions for graph traversals. So for example, if I want to find all the outgoing neighbors of vertex 2, what would I do? It's like, okay, first I find all the edges which are incident as sources to vertex 2. So we just saw that. And then I just take the targets of those. And so you can see that that is indeed exactly how the outNeighbors function is implemented in Catlab. So like I said, all these basic graph traversals and accessors and mutators end up being basically one-liners. Okay, so I want to talk a little bit about like, what is the data in a CSET? How is it implemented? So basically the way it works is that for every object or type in your schema, you then get a table in your CSET. So we can see here that there are 2 tables. associated with this graph, one for vertices and one for edges. So in this case, the vertices have no attributes or subparts, so that the table corresponding to vertices is trivial in the sense that it has no columns, so it's sort of a degenerate table. But the edge table has 2 columns, and so we can actually pull it out and see what it is. It is just a table, like we saw printed earlier. So tables are one of the things in C sets. The other things are indices, like I explained. And so these are sort of an implementation detail, but they're tracked. And so that, like I said, is what allows the incident function to quickly look up these pre-images. And so if you're familiar, if you've worked in computer science, you've probably heard about the different kinds of representations you can have for a graph. So what this really is just like a generalization or a systemization of the adjacency list representation of a graph. So now all of this would be a lot of pointless abstraction if the only thing you could do with this were graphs. But thankfully, actually, there's a whole lot of things that fall under this rubric. That is, that you can obtain as a C set for some suitable category or schema C. Let's look at what some of these are. So
any questions before, like moving on?
So I'm just having a hard time. Again, this might be a dumb question again, but I'm just having a hard time conceptualizing what could be stored within each of the vertices and the edges, because it seems like you're saying a particular table could be stored in an edge or a vertex.
That's right. So in general, like for every object, there's a table. It just so happens that for this particular schema, like the vertex table is not very interesting. Like it's essentially just keeping track of a single number, which is the number of rows that it has, but the rows are all empty things. I don't know if that's a helpful comment at all.
And I am assuming that how the graph is shaped would then represent the relationships among the different forms of data, because I'm assuming there could be could be typical tabular data, or this could be JSON format type data.
Yeah, pretty soon we'll see some more schemas, and we're going to see several more schemas in this talk. So maybe that will help clarify like what is the kind of the space of possibilities that you can have here. Yeah. So for the moment, I'm just going to say that here are some of the different things that you can represent as C sets for some C. And I'm not going to actually do these examples. I just want to give you a sense of like what are some other data structures that fit into this framework. So you can do different flavors of undirected graphs. I say undirected in quotes because from a category theoretic viewpoint, you have to unpack that a little bit. But basically, you can do symmetric graphs as well as these things called half-edge graphs, which are almost the same. You can do more kinds of graphs like bipartite graphs. You can do what you might think of as a souped up form of graph, which is a wiring diagram. So those have ports and an outer box, and we won't talk about that much. You can do a certain flavor of Petri nets, and I'm just now starting on a new package that will do simplicial sets, which are basically things like meshes, surface decompositions and stuff. But there's a lot we could talk about there. It would be a lot of fun, I think, but instead we're gonna shift gears a little bit and then talk about data frames and how that fits into this story instead. So I'm just pointing out there's sort of an alternative path that you could explore later. So, okay, so what on earth does data frames have to do with any of this? So one way you can think of if you want to think about a data frame sort of diagrammatically, we were thinking about the schema for graphs diagrammatically. You could say that if I have a data frame with k columns and n different rows, I can think of that as a multi-span of functions. So that's just kind of way of saying that it's a particular kind of collection of functions. So in other words, there's an object in here which just represents the numbers 1 through n, and then k different functions, and those give the data in each column. And so that's one way to start to think about this. And so from then you could say, okay, well, we could then incorporate data attributes into C sets. One particularly simple thing we could do is just say, okay, I'm going to add another object to the schema for every one of these sets A1 through AK where the attributes live, and then add some morphisms that correspond to the columns. And I think from a certain point of view, that's a fine way to think about things. In practice, you often want to treat data attributes, so things like strings and stuff, different from the IDs that correspond to vertex and edges. Because after all, like in our implementation, I've said that things like vertices and edges need to be consecutive numbers, but attributes could be anything. So we want to treat that differently. And there is kind of formalism for things like that. I'm not going to get into the formalism because it goes a bit beyond sort of categories and functors into more advanced topics in category theory. Instead, I think we can just sort of look at how it works in schema. So now we're going to look at attributed C sets, which extend the C set formalism with data attributes. So as a simple first example of this, we're going to look at weighted graphs. So a weighted graph is usually defined to be a graph whose edges have numerical weights associated with them. Okay, so in our schema, we've previously seen objects and morphisms. Now we're going to look at the two other kinds of things you can have. You can declare a generator for data. So this basically represents a space where the attributes live. And then I can use attr to specify an attribute. So I'm going to say there's some type for the weights, and then there's actually the weights themselves, which are attributes on edges. Okay, so to instantiate this as a Julia data type, I would call this function adject type. But once again, I'm not going to actually run this code because weighted graphs also comes with Catlab. So I'm just going to use the type that comes with Catlab. Okay, so one thing to note here is that this actually generates an abstract type where I could say like what I want to fill in this attribute as. So I'm going to say that I'm going to instantiate a weighted graph, putting float here to say that my weights are 64-bit floats. And now I'm going to add my vertices and edges, but this time I specify the weights, additional data. So now my edge table is expanded to include weights. So I didn't do it here. I could have also put some kind of attributes on the vertices. Maybe that would have been a better example, because then you'd see how the vertex table would cease to be trivial. It would then have some stuff in it. But I guess here we're just sticking with edges. Okay, and so you can now kind of treat this as like a data frame that's sort of attached to a graph in a way. So for example, I can pull out this column weight. I can assign elements of it. For example, here I'm going to set the third edge, the last edge, to have weight 2.5, and I can see that happens. So it's all pretty intuitive if you've sort of worked with data frames. So, but now it's sort of attached to this graph. So there's just a technical note I was going to do here. I don't know how much time I want to. All right, I'll just say something very brief about this. So this is a distinction that's really unique to Julia. So like this doesn't really come up in Python, but because Julia is actually a compiled language, it's just in time compiled, but it's compiled nonetheless. There's flexibility about how much information you encode in the type of an object versus how much is purely a runtime sort of factor. And this actually can affect performance significantly. So just sticking with tables themselves, like there's an approach to tables in Julia where you actually encode all the type information about the table, both the number of the columns and their names, as well as the actual data types they have, all into the type. And there's also there's a different approach where the type for data frames doesn't include the information, and the columns are just whatever you get at runtime. And that's actually what the package dataframes.jl, the kind of the default one, does. So because in Catlab so far we've mainly been concerned with like relatively small structures, things like graphs, we've actually taken a static approach so far. So like when we instantiate this Julia type here, I'm calling attribute type to get this weighted graph, it's actually generating a Julia type that has fully encoded the schema that you saw. And then we use basically a form of metaprogramming to generate the accessors and mutators for that data structure. So the advantage of this is that like it leads to very efficient, it leads to very fast data structures, because it sort of has the effect that like the graph type that we end up getting is more or less what you would code up by hand if you were to implement a graph using an adjacency matrix. So that's great, which means that we can use the graph like as if it were sort of a first-class thing. The downside to this is that this static approach doesn't scale well with large schemas. So like if you had a database with like, we'll get to more databasey stuff shortly, but if you had a database with large schemas, you would end up with huge compile times and weird stuff. So that for that, you would want to use a more dynamic implementation. We don't yet have that, but if there was sufficient interest, we could eventually explore that as well. So if that made no sense, it's sort of a technical side note, and we need not become bogged down in it. Okay, so now I want to
with a degree of comfort that President Obama didn't have.
Okay, so so let's start with now like a more a data-centric example. So I'm going to take as an example data set this Sitka is how you say it. I don't know. It's about a certain kind of spruce tree. It's a data set from the R package mass, and it basically contains in it measurements over time of the sizes of a certain set of trees, which are classified into treatment and control. One gets like an ozone controlled environment or something. So if I load this up as a data frame, this is what it looks like. There are 4 columns. And so thinking about, so from the viewpoint of multi-spans I gave above, this data table would look like a span, multi-span like this. But the point I want to make here is that this is an example of longitudinal data. So like data made at repeated measurements over time. And such data actually, although it's often represented as a single table, in some ways that's not quite right, because structurally it actually has 2 levels. So there's 2 sets of things that are involved in this data. There's a set of trees, and then for each of those trees, there's a set of measurements. And moreover, both the trees and the measurements have data attributes. So if we wanted to have a representation of this data which is more faithful to its underlying logical structure, we would, and if we were ignoring attributes for the moment, our schema would be this. We'd have objects for trees and measurements, and there'd be just one generating morphism from measurements to trees, which tells you what tree that measurement is associated with. Okay, so but to instantiate it with all the attributes, we could do something like this. So so there's trees as one object. Each of the trees gets assigned a treatment. So this treatment is an attribute of the trees, not of the measurements. And then there's the actual measurements themselves. So here's the morphism that is in this schema. So function from measurement to trees, and then there's the size and time attributes for the measurement. Okay, and so I'm going to load this data into my C set. Okay, so step 1, and I'm going to go a little bit faster here. So you may not have time to fully study the code. I'm going, after the talk, I will make this notebook available so that you can play around with it at your leisure if you're so inclined. So basically, we just need to add, so the main thing to do here is we need to check that the the numbers of these trees, we sanity check that these are indeed numbered 1 through n. Having checked that, we can just add them. And then we also add the measurements, which correspond to the rows of this table. So this table, when you think about what's in this table, it's actually the measurements. So we end up with a C-set with 79 trees and 395 measurements. Now, one thing that we didn't assign here, we didn't actually assign the treatment that each tree gets, because it's in the table that's actually associated with the measurement, but it's repeated. So we actually need to check for consistency that each tree is only assigned a unique treatment in the data. So that's what this only unique call does. That will throw an error if there are conflicting assignments. But having done that bit, we end up with this. So I'm showing here the tables from the resulting C-set. So we have the treatment table is simple. It has only one thing in it. Or sorry, this is the tree table. It has only one thing in it, which is the treatment. And then there's the second table, which corresponds to the measurements. Now, the point I wanted to make here is that what is the utility of the schema? The utility of the schema is that it ensures that it is only possible for a tree to have a single treatment purely by virtue of the structure of the schema. So you can enforce certain, the schema alone, even in the absence of any equations, can enforce certain logical requirements. And that's something that you couldn't actually enforce that in the data frame without actually verifying that it holds, okay? So, and this also is a slightly more compact representation of the data because you don't repeat the treatment for every single time it occurs with a measurement. And so I would argue that it would generally be good to store longitudinal data this way. For some reason, people don't always do this. But with the right tools, the other point I want to make is with the right tools, it's really easy to get back a data frame if you want one. You just need to do a certain kind of query that will join these back together. So we're going to talk more about queries later, but I just want to just show very quickly here, without explaining how the query works, that indeed I can define this query and then execute it against my C-set that I constructed to recover the original data frame in just a few lines of code. So like there's no, so again, the point I want to make, there's no real disadvantage to storing your data this way. You can always sort of blow it up to get different views. But to illustrate the queries in a more interesting way, I think it would be good to have a data set which has a more complex relational structure than this trees data. So we're going to look at another data set now. This is the Mutagenesis Data Set. It's kind of a popular benchmark data set in like relational machine learning kind of world. And it now, instead of having it's from a study on how much certain chemical compounds encourage mutations. And so instead of having a 2-level structure, it actually has a 3-level one now. So we have at the bottom molecules, and each molecule can contain atoms, and then atoms in turn can be bonded together. Okay, so again, without attributes, we have a schema with 3 objects and 3 generating morphisms. So every atom belongs to a molecule, and every bond goes from one atom to another. Okay, and so the complete schema associates some different data attributes to these different things. So like, for example, we won't go through them all, but like, for example, like there are some indicator variables associated with a molecule. Atoms are assigned like what element they have, and then like what charge corresponds to it, things like this. Okay, and below here, there's some data munging to load this stuff in from a SQL database. This is a sort of thing that can and should in the future be automated. So in the interest of time, I'm not going to skip it, but if you if you want, it's all here. We basically load in the 3 tables from a SQL database and then stuff it all in to this C set. But in the interest of time, let me not dwell on that. What we end up with is a C set with 188 molecules, about 5,000 atoms, and also about 5,000 bonds. So again, here's what the tables look like. Molecules, atoms, and bonds. Okay, so the first one interesting thing about this data set is that its structure is basically that of an indexed collection of graphs. Like for every molecule, you have a graph where essentially the vertices are the atoms and the edges are the bonds. And so one thing you could say is, well, okay, like, can I construct that graph? And the answer is yes, you can very easily using Functorial data migration. So in Catlab, we don't have a full implementation of Functorial data migration, but we have sort of it in the simplest case, the so-called delta migration, which is sufficient for this purpose though. So we can say, okay, the vertices correspond to atoms, the edges correspond to bonds, and then the source and target correspond to like atom 1 and atom 2 in this schema. And then having made that mapping, I can just in one line construct this graph. And we'll see that we end up with a graph which has the right number of vertices and edges matching the data above. And then the connected components of this graph correspond to molecules. So there are 180 molecules, and indeed there are 188 connected components. So so converting to a graph would mainly be useful if you have routines that expect to get a graph as input, but it's less useful in Catlab than it might be in other systems because graphs are really the same type of thing. They're all C sets. So like you can still do most of the things you could do with a graph just directly with the original data. But of course, there are always going to be graph algorithms that are implemented in terms of the vocabulary of a graph. So this shows that you can easily get that if you want it. Okay, so now we're going to turn to the final topic of this talk, which is conjunctive query. So now we're going to really see the connection and analogy to database technology. So conjunctive queries are a lot of things. So like in practice, it's a kind of a core subset of the queries that you can make in SQL. They're studied a lot in relational database theory as being like a particularly well-behaved class of queries. From a logical perspective, conjunctive queries are the kind of queries that you can express using the subsystem of first order logic that gives you basically existential quantification, conjunction, and like true constant, sometimes called regular logic. And they're also, so that's sort of technical thing, but sort of from a more intuitive perspective, what's really nice about conjunctive queries is they have a graphical syntax that corresponds to undirected wiring diagrams. It's a very intuitive graphical picture that goes with them, and we'll see that shortly. Okay, so in Catlab, unlike in some other systems, conjunctive queries are actually represented by undirected wiring diagrams. And so you can create them in Catlab any way that you can create an undirected wiring diagram. The simplest is to use this macro called relation that we'll see. And then we've implemented a basic query engine for evaluating conjunctive queries against attributed C sets. So rather than going into like the math to say like in general what a conjunctive query is, I'm just going to try to show you kind of by example what they do. And if you're familiar with SQL, it's very similar to that, although it's the syntax will be different, but same underlying concepts of joins. This is the key operation that's being performed. So, okay, so as a first query, we're going to be working with this mutagenesis data. So we're going to find all the bonds between atoms that are in the same molecule. So so one motivation for doing this is that like as a requirement of logical consistency, a bond should only be between two atoms if they actually belong to the same molecule. So we should expect from this query to actually get all of the bonds. And so we're going to sanity check the data here. Okay, so here's what the query looks like. So so basically, there are three sort of relations. So here we're now thinking of each table as being kind of like a relation. So like a bond is a relation between atoms. So I'm basically looking for, so let's look at the picture. So the dangling wire here represents the output of this query. So it'll be a bond. And then I'm going to look for bonds that have atoms that are connected to the same molecule. So the enforcement of the constraint comes from the fact that like the molecule of atom 1 and atom 2 are both assigned to be this variable m, which is the same thing. Okay, so when I run this query, it would be disturbing if it didn't give me a length, if the number of results was not just the same as the number of bonds in the data. Fortunately, that's true. So that's good. So given that, this is sort of tangent, but given that, this would actually be a good constraint to add to the schema. So I said that schemas can have relations or equations in addition to generators. So I could put this constraint into my schema. And right now in Catlab, such constraints don't do anything. Like they don't change the behavior of anything, but they are good documentation and among other things. So okay, so next query. So we could ask, okay, one would think that this graph should sort of be undirected in the sense that like bonds should connect to atoms in a symmetric way. So you might think that, okay, let's see if the data is like that. So we're going to look for pairs of atoms that have bonds going in both directions, so like edges in both directions. So we can do that using this query here. So you can see that they have two outputs, both atoms, and then I'm just checking for bonds that go in both directions. But in fact, this query is empty. The result set is empty. And so actually so I don't know, I'm not a chemist, but I guess my best guess is what that means is that like this graph is really like kind of a presentation of a symmetric graph. Like you're supposed to imagine that the arrow goes both ways, but in the data it only goes one. I don't know, maybe that's just my guess. In any event, let's keep going and look at a few more queries and then we'll wrap up. So so now we're going to look at a query that can find directed paths in these molecular graphs. So we could formulate this query either against the graph that we constructed, or we could formulate it against the actual data, just to show how we could use this machinery of conjunction queries on graphs themselves. I'll first show that like, okay, I can take this query here, which finds edges like a path of length 2, and expressed in terms of vertices and edges, and run that on the mutagenesis graph that we constructed by Functorial data migration. And we'll see that we get, over 5,000 results in this query. But it's more expressive to formulate this against the original data. And by doing this, we can actually include more kinds of constraints. So here I can say, we're going to find all the directed paths that go from a carbon atom to a nitrogen and then to a carbon. And so this will actually illustrate the use of query parameters. So now I've got this bigger query where I can see, so this is, and then I'm going to check that the elements have certain values. So these terminate here in dots, and so these I will fill when I run the query. So carbon, nitrogen, carbon, and then I can see that I get a much smaller result set. Okay, so that was a lot. But to conclude, so if you take nothing else away from this, like I don't know if you want to use Julia or not, but if you take nothing else away from this, I hope it would be the idea that although graphs and data frames and relational databases are often treated as if they live in totally separate universes, they don't have to. There's no fundamental reason for this. And in fact, category theory provides a nice mathematical language in which to understand how they're all sort of manifestations of the same concepts. And then we are building on that mathematics to implement this in a concrete way in Catlab. And when I say we, I want to acknowledge the other people who have contributed to Catlab. So these being James Fairbanks at University of Florida, Andrew Boss and Micah Halter at the Georgia Tech Research Institute, Sophie Lipkind at Stanford, and Owen Lynch at Utrecht. All of them have made contributions to this work. And to wrap up, I'll mention where you can read more about such things if you're interested. So first of all, I'm going to make this notebook available after the talk. The second half of this talk was based mostly on a blog post that I wrote. So, and that blog post also goes into more technical detail about how conjunctive queries are implemented, and the deep relationship between conjunctive queries in the world of databases and limits in category theory. So the short answer is that they are finite limits and FinSet are pretty nearly the same thing. So there's a bit about that on the more technical end. So yeah, beyond that, if you want to talk to me or other developers, we have a channel in the Julia Zulip. Happy to talk to anyone who's interested. So thanks so much for listening to the talk today, and I'm happy to take any questions in the time that we have left. I don't know if I'll stay for as long as people want to ask me questions. So
there's 2 in the chat right now.
Okay, so. Okay, so is Cat, yeah, so right now how does the internal query implementation take advantage of categorical semantics? Okay, this is a good question. Okay, so in Catlab, we have, so if you're familiar in category theory with the idea of limits and co-limits, this is like, these are particular constructions in category theory that you can apply in all sorts of different categories, and they are very well behaved in C-sets, and we've implemented them. So, and we've implemented quite a bit of machinery to compute limits and co-limits in set as well, because that's what you need to implement them in C-set. So actually, like one way you could say that finite limits are conjunctive queries, but we sort of turn that around. We actually implement limits as the primitive operation and efficient algorithms for that, borrowing some ideas from database theory, and then we use those to implement conjunctive queries. And one advantage to doing it this way is that limits are useful in other settings as well. So like the same machinery that we use to implement conjunctive queries, we can use to implement other kinds of categorical constructions. So there really is kind of a nice interplay between database theory and category theory. Like on the one hand, category theory shows how ideas from database theory can be generalized to all sorts of other settings, but databases, people in databases have spent a lot of time figuring out how to do conjunctive queries fast. And so our implementation of conjunctive queries it's not going to compete with like Postgres or something, but like we do borrow some basic algorithmic techniques from databases, and over time I expect that will improve. So it's really kind of a fun interplay between ideas.
questions?
I have a couple questions, two short ones, one maybe a long or one not. So the first two is, this seems like doesn't have to be this idea doesn't seem like it only has to apply to relational database. It seems like you could generalize non-relational databases enough to extract some kind of graph structure.
Yeah, that's a good point. I didn't mention like graph databases specifically, but in a way, I think that like graph databases and relational databases are like not as different as people sometimes suggest. Now, when talking about stuff that's further away from that, like document-based databases, that I don't really know what the mathematics of those things are, so I don't know about that. But like, definitely, graph databases is like would be related to this as well. So thanks for saying so.
Yeah, and second one is, actually I forget the second question, but so I'll move on to the last. Could you explain a little more exactly how Catlab extracts the underlying graph from
Yeah,
a particular
like-
database? Because don't you have to explicitly?
You're talking about this
program that in?
this part here, this one?
Yes.
Yeah. So you're right. There's no magic here. So like Catlab doesn't know on its own that like, oh, like the molecule, the bond atom structure is the same as a graph, and then just know to pull out a graph. So you're right about that. You do have to specify the mapping, and so that's what we're doing here. We're actually saying the vertices are atoms and edges are bonds, but then with this, but that is enough to determine this data migration. So you do have to specify the mapping at the level of the schemas, but then the software can actually move the data over in the right way and give things the right names. And you can have mappings that are more complicated than this. Like, so this is a simple mapping where, just generators go to generators, but like morphisms and categories can compose, so you can actually send things to composites as well, which so I didn't give any examples of this here, that it's a bit more complicated than what we're doing here, but just to point out that like you can, even this delta migration functor, which is the simplest of the three functorial data migration functors, you can get a fair amount of mileage out of even it. So.
But you would have to explicitly program things in there.
Yes, you do have to specify the schema. Now, I mean, it's not out of the question. I mean, yeah, you have to specify the schema mapping. Now, it's not out of the question that like, you can like do pattern matching on your schemas to find out that like, oh, this schema I have has a subcategory which is isomorphic to this other one, and then, but how to actually make that useful, and I don't know. But maybe there is stuff to think about there. So
yeah, that's right. I actually remember the third question that I had was,
okay, great.
Relational databases. I mean, you could have different tables, and you can kind of cross-reference them by their keys.
Mm.
Is there something similar in this representation of data?
So there is. So let's look at this data here. So in most SQL databases, you can kind of make anything you want the primary key, and then it's the database's job to figure that out. We take a more like a restrictive point of view, where like these part IDs I was referring to earlier, like those act as the primary keys, and then like the morphisms in the category are what are like the foreign keys. So for example, like this table for atoms, like atom 1, sorry, this table's the bonds. So for these bonds, like atom 1 and atom 2, like what are these numbers? Like these are basically the foreign keys, and those refer to like the rows in this table. So actually this first atom is just 1, and so it's actually this first row here in the atom table. Yeah, so yeah, you can definitely think about it in terms of primary keys and foreign keys if you like that sort of terminology.
Other questions?
I have a question. Evan, are you at all familiar with the ontology language called OWL?
Yes, I am.
So are some of the OWL constraint parts of the language expressible as the constraints that we just saw in your talk?
Yeah, this is a good question. So yeah, so this isn't exactly the question that you asked, but let me first say that like in the case of like RDF, and you know, RDF can be viewed as a kind of graph database, so it fits pretty well into this sort of way of thinking. OWL is kind of a different beast because it's a description logic, and they're very sort of relational in character, but in kind of a different way. So I I actually wrote a paper about how description logics like OWL can be understood sort of category theoretically, and so you can think of them in terms of categories and functors, but you kind of want, this is my viewpoint on it, you kind of want a different kind of category so kind of category called a bicategory of relations. And so like a C-set doesn't implement that exactly, but I still think there's actually quite a bit to think about in terms of, like, I don't know the full answer to this question or what the full story is here, but in terms of understanding the relationships between like description logics like OWL and relational databases. I don't know, Ryan, do you have any thoughts to add about that?
How could you send me a reference to your paper?
So if you send me an email, I'll send you a link back to the paper.
Is your email-
Or actually, I mean, I can. Okay, if someone else wants to ask a question, I can put in a link to this paper into the chat. Let me just do that right now.
Did you do that?
I'm working on it at this
Okay.
one
Okay.
second. So, okay. Oh, why does it say direct message? Sorry, I just direct messaged someone. Okay, sorry about that. Here's the paper. Okay. Any other
Thanks.
questions?
Not a question, but a comment, and it might be relevant. On the topic of non-relational databases, I believe that some category theory was used to create libraries such as LINQ, L-I-N-Q, in order to like have a common language between SQL and NoSQL and stuff like that. And I included a link in the chat.
Oh, thank you.
Oh, cool. Thanks. Yeah, I don't know that I'm familiar with this. So thanks for that link. I'll check it out.
And there were some other comments in the chat that maybe should be read out loud. Does uniqueness of a tree boil down to finding isomorphisms in graph terminology.
Okay, let's see what this. Just uniqueness of a tree. I don't think so. This is really more of a just a data consistency requirement that's specific to this data. I did point out how you can be encoded as the way I would think about it is let me find the relevant place. Right. It's like in the schema or the category, however you want to think about it, you would want to have this equation which basically asserts that two morphisms are equal. So the composite of the morphism atom 1 in molecule is equal to the composite of the morphism atom 2 with molecule. And so that changes the category, and it changes what's valid data, what would be valid instance data for that schema. Yeah. Someone asked, is Catlab the only dependency? It's the main dependency for this notebook. If there are a few other things you'll see in here, like data frames and stuff like that. So actually we can look and see. Here's the project file, which says what packages I'm using here. So some SQLite, my Tixie for my diagrams, but the core thing here is Catlab. The rest of this is just sort of extras that I needed for this notebook. Anything else? Oops.
So I keep asking questions.
No, that's fine.
Because I
That's
haven't.
great.
I mean, I have absolutely no idea what calculus theory is really, but from a really engineering or practical point of view, what are the advantages of representing data in this manner? And asking the same question from a mathematical point of view, are there specific circumstances or conditions in which this kind of representation leads to better run times or memory efficiency?
Yeah, I mean, my take on that question is this: like, there are certain very standard data structures that exist in basically every data analysis ecosystem, like data frames and graphs, and those are great things, but they don't actually always good ways of faithfully encoding your data. And you pay a price for that in various ways, as I tried to indicate at certain examples in the talk. And so what Catlab basically provides is like a toolkit for like basically defining your own data structures, but in a way that requires that's like basically declarative. You specify the schema and then you get a data structure. And so then you can basically draw on the full strength of the relational model, as well as getting various category theoretic goodies like functorial data migration, without having to implement it all yourself. So it really so my hope for this work is that it will lower the barrier to entry for people who want to kind of work with relational and category theoretic constructions like with their data, and to expand the toolkit that data analysts have beyond sort of the familiar abstractions of graphs and data frames. That's how I would motivate it.
I guess I'm really asking this as a data scientist. Again, this is my opinion really, but I wouldn't. I mean, I just want to grab the data and go and run it.
Yeah. Yeah. I mean, it depends how you look at
Is
it. Like, so for example, a lot of time, so I think a common workflow, I mean, different people have different workflows, but so I don't know what yours is, but a common thing I've seen is that like when data scientist gets data, they might initially do like run some query or have a DBA run some query against the SQL database, and they get one big honking table. And then after that, they load it into R, and then you just have to work with that table. And so in effect, like if you want to do further queries or transformations, like you essentially have to do it yourself, like using like the join function that you have in like dplyr or whatever your toolkit is. Whereas like these tools provide a more declarative, like conjunctive queries is a more declarative way to do that stuff. Like you don't tell it how to do what exact sequence of joins to do. That's the job of the query planner to figure that out. You don't tell it exactly how to build like the data structure you need. Yeah, so I think, yeah, I mean, I personally think there are advantages in reliability that you get from encoding your data in a way that is faithful to its structure. And sometimes just having a single table doesn't do that. Like it allows you to get more, allows you to introduce consistency errors, or it requires you to blow up the size of your data just because you have to basically expand it all into one table. And so I don't know. So these are some of the advantages I see. But yeah, I mean, I don't,
So are there some measurable metrics around?
I mean, there's no
like,
usability studies
runtime
if that's what
memory
you.
efficiency.
Yeah, I mean, so we have some. We have some
like,
benchmarks in the Catlab repo, which demonstrate, for example, that like the graphs module in Catlab, which is implemented using this general machinery, achieves like decent, not as good performance as light graphs, but it would be, for example, much faster than NetworkX on basic graph operations. But it's also worth pointing out that, I mean, like, I think these tools are starting to get more usable, but this work has still some of the character of a research project, in that, like, I think some of the things we're doing are not standard. So like, over time, they'll probably change and evolve as we figure out how to make them more usable and more useful. So, I'm not saying that, we have software which has the same degree of being tested as like Pandas does or something, but I also hope that we're exploring some interesting ideas that could eventually become more part of the toolkit of data analysis, but that right now is not very much, frankly, it seems to me.
Because then I'll be interested in seeing again. I mean, from an academic point of view, I mean, this is interesting. This is completely something new. But then from a practitioner's point of view, I mean, I would really love to see like how it does compare. Okay, how does it compare in terms of their memory efficiency, runtime efficiency, as well as the brevity of the code. And also there's a learning curve when people are first learning about tabular database formats. There's a learning curve around it.
Yeah, I don't disagree with any of that. Yeah.
Evan, I had a question. It's kind of loud here, so I typed it. But where would be kind of the first place you'd expect to encounter performance or scalability bottlenecks as you take the framework and start to apply it to really large data sets?
Yeah, so there are two sort of directions, at least two directions of scalability, I guess. One is like the size of the schema. So I already mentioned that in the current implementation, it's really optimized for smallish schemas. Like if you had a table with like 1,000 columns, that's going to put a lot of strain on the compiler and probably not be a great approach. So eventually we'll probably want at least 2 implementations of this for those different scenarios, or maybe even ones that mix and match the dynamic versus static. But the other direction is like, but assuming for the moment you have a small schema, things right now are pretty fast, because like, when you, my Zoom is blocking my. One second. Okay. So like when you call these things, these accessors and mutators, it looks like you're passing a symbol. Well, you are passing a symbol. So you would think that this would have to be like resolved at runtime. Like what exactly do I do with this symbol? What table is it in? So forth. But in fact, those things are like resolved at compile time, the first time you call this. And so it's as if you're basically calling a specialized function for this data structure. And so that eliminates like a lot of the overhead that you get from like, that you might expect to get from having this more generic approach than just having like a single graphs data structure. So that's good for performance. Now I haven't done, so another area where you would start to run into limitations of our current approach is like, I haven't worked in settings where the data would like exceed the size of the memory that you have, nor have I, like, we have not really optimized this for like memory like usage. So I'm sure I'm sure there are places in the code where like we could tighten things up and stuff. So like, but one thing that's sort of neat about our implementation, so I mentioned that Julia has various kinds of tables. So like the tables that the C sets use under the hood can actually be anything that implements the tables.jl interface, which is a generic interface for table tables. So like probably more work would needed to be done to make it actually like work properly. But in principle, there's a path to having like tables that are like not like that are distributed, for example. So yeah, so there's all sorts of directions there. So I would say that like, but that sort of gives you the sense of where things are currently, I would say.
Yeah, thanks. Really interesting. Thanks for the presentation.
Thank you.
Yes, I have a question in regards to like enforcing equations on C sets, and so are there any areas in which like Catlab might be insufficient, either performance or expressibility wise, compared to like a compiled language or a dependently typed language such as like
Yeah.
Haskell or Idris or Agda, respectively?
Yeah. So
Yeah.
yeah, so there's a couple different questions there. On the topic of language, there is no best answer to the question. There is no unique answer to the question of like what language should I use to implement stuff in. So we chose Julia because I think it's kind of in a nice middle ground of being able to be like reasonably performant compared to a language like Python or R, while also being a lot more sort of easy to use than something like C, and being, so I'm personally interested in like aspects of scientific computing and statistical computing. And so Julia is well integrated with that world in a way that say like Idris is certainly not. So, of course, but it's sort of, there are benefits to using, there'd be benefits to using a more fully mainstream language like Python, which is just that people know it. there would be some benefits to be had from working in Idris, but you also pay a large price for that. So to me, there's no simple answers. There's just trade-offs. But on the whole, I think that Julia works pretty well for this, and we do take advantage of some of its unique features, particularly like its meta-programming capabilities to implement CSETs. So like you couldn't do this very easily at all in Python, at least not if you wanted to get the kind of performance that we do. Then I think there was maybe some other aspects to your question.
Equational constraints on.
Yeah. Oh yes, right. So the other part of your question was about like expressivity of those things. So I didn't really emphasize it in this talk, but there's sort of a categorical logic perspective on these things where you can think of, like if you think of, instead of thinking about schemas, you can just change perspective a little bit and think about the categories being like a theory. And then the instances aren't databases, they're models of the theory. And from that perspective, C-sets actually sit at like the bottom of a hierarchy of sort of logics. So like the logics, the quote unquote logic that you get in just a category is like not that expressive. And so for example, like you can add more bells and whistles to get things like Labir theories, which are like algebraic theories, or you can add sums to get, unions of, there's a whole sort of world of things to explore, sort of going beyond this. All I can say about that is that I think there's lots of cool things to do there. So, and not enough time to do them all. So.
One more quick question. There's certain similarities between your work and Ryan's CQL, categorical query language. Have you ever given any thought to any kind of integration between the two, or?
Yeah, I mean, it'd certainly be neat to consider. I mean, I think that the CQL is sort of in a different part of the space, like focusing on like SQL databases and like large scale data migrations and stuff, whereas this is mostly sort of like in memory and like sort of more designed for like that kind of computing. But that means I think that those things complement each other well. And so, yeah, I think that'd be a cool thing to look at. So.
Any other questions?
This is more of a mathematical question, but can all tables be represented as graphs? Or maybe that's a trivial one. I'm not actually sure.
Is the question, can all tables be represented as graphs? I'm not sure. I'm not sure I understand the question.
Well, can all tabular formatted data can be represented as graphs of certain form or another? Because you might not have any.
Yeah, I mean, in a sense they can be. I don't know if you're familiar with.
Or in a connected graph, maybe that's construing that.
Yeah, I mean, so there is this construction called the category of elements, or the Grothendieck construction, which can take a C set viewed as like a set of tables and turn it into something that looks like a graph database by basically blowing it up into one gigantic graph. And that's one of when I said earlier that like graph databases and relational databases are not like totally disjoint worlds. That's partly what I was referring to. It's a bit much to just explain in words how that works, but if you want to look up like category of elements, you can. And I think David talks about this in his book too. I'm pretty sure he does. So, yeah.
Because then some use cases I'll be thinking of is, let's say I have a particular gigantic data table that
Mhm.
will represent as some kind of a graph, because
Mhm.
for some reason I decided I think it's going to be useful. But then I realized, okay, there are three distinct buckets, and those three distinct buckets of features aren't necessarily related from another. So I may be able to represent the entire data in three separate graphs. I mean, would that even be helpful if I'm writing queries on top of that?
Yeah.
How would that
Yeah,
play
without
out?
understanding more about the particular circumstance, I don't know. I'm not sure what to say about that.
But let's say like the graphs, the three graphs, there's no way that I can connect those three subgraphs.
Hmm.
No edges flowing between one of each other. Or is that not?
I don't see how that's like an
too
essential
abstract?
aspect that would affect this. Like, yeah. Yeah, sorry, I'm not really sure how to address that question.
Or maybe let me try to ask this another way. In order for me to run a query on top of a data that's structured in this particular way, does that graph needs to be connected?
No, it does not need to be connected. Like, for example, like if you could like take your schema and have like two different objects that don't have any morphisms between them, then in like the corresponding graph database, like take the category of elements, like those will be disjoint. Those will be in different connected components of that graph, and that's fine. It doesn't change anything about the way that queries work, really. But I see there's another question in the chat, so let me answer that. So someone asked, I'm interested in reading or hearing more about the query planner implementation. Do you have any references? Yeah. So the first thing to look is in the blog post that I link at the bottom. If you go to algebraicjulia.org, you can find the blog there. And at the end of that, it does go into some more details about a little bit more details about the query planner. But the honest answer is that the query planner right now is quite primitive, and so we need to get some. So it works fine on these simple examples that I gave, but it's a project for the future to build better query planning stuff. So actually that's people want to contribute to Catlab or interested, that would be a great thing to work on. Okay, so maybe we should wrap up here.
So Ryan had to drop off.
Okay.
On behalf of Ryan, thanks very much for presenting, Evan. Any final thoughts from anyone before we close the meeting? Okay. Then.
Okay. Well, thanks a lot, everyone, for coming. Hope to talk to you again later.
Thank you.
Bye.